So what we got here? Well, remember we were calculating last time at the end surface area. So that's where we're going to continue. And we're looking at the surface area, and this formula here at least would work for this situation. So if you have a function y equals f of x, and you rotate it about the x-axis, the surface area, the curved part, you get by finding this pretty massively ugly formula. And it tends to involve, doesn't it, differentiating, squaring things, foiling things, collecting things, and 12 lines of algebra later, you finally get something you can work with. Then you plug it in here, and then you've still got what, u subs to do perhaps, maybe even an integration by parts. And that takes another 10 lines. 20 minutes later, you've finished one question. And that's kind of how they work. Well, here are some more situations. If you want to take the function y equals f of x, but you want to rotate it about the y-axis, right, you could do that, rotate it about the y-axis, the surface area is given by this formula. Now, if you look at this one and you look at this one, do you see they're almost identical? So 90% of the work's going to be the same. Do you see the only difference is 2 pi x and not 2 pi f of x? So you're going to have some questions where they give you y equals x cubed rotated about the x-axis, and then y equals x cubed rotated about the y-axis. When it's the x-axis, you remember to use this formula. When it's the y-axis, you need to do that one. So I suggest that you write these little things in cards or whatever that you do to try and remember, and say, okay, what's the situation in this question? Is it rotating about the x? Is it rotating about the y? And choose the right formula accordingly. But that means there's 4 formulas. So here's number 3. I haven't done any of them, but will today. Suppose you rotate a function like x equals y squared plus 1, and you want to rotate it about the x-axis. This is your formula. And if you want to rotate it about the y-axis, right, x equals y cubed, whatever, about the y-axis, this is your formula. Now you look at these formulas, they're almost the same. Do you see you have that little y, g of y difference? Do you see how the derivatives are very similar? The bit inside the square root. So you've got 4 situations. A function in terms of x being rotated x and y. A function in terms of y being rotated about the x and y axis. Okay. So what we're going to do today is we're going to have a look at ones that look like these 3. So a lot of the math is going to be the same kind of things, right? The same kind of math. Let's find one. It's about the x-axis. It's about the x-axis. About the x-axis. Here we are. Let's do question 7. Well, similar to 7. It's going to be y equals 1/3 x to the 2/3. So that's the curve. X is being between 0 and 12. I hope that works out well. And you're rotating about the y-axis. Which means this one. Okay, so here's my function. There's my limits. Rotate about the y-axis. So I'll kind of go through the same kind of sequence of events that we do in every single question. Right, there's the original. Going to find its derivative. Right, if you multiply by the power and reduce it by 1, you get 2x to the power of -1/3. 1 plus the derivative squared is next. So that's 1 plus, oops, no. Squared. 2 9 squared gets you 481. x to the negative 3 squared gets you x to the negative 2/3. Oh, yeah. I did not swear there. But I did scan badly. For some reason, 2/3 turned into 3/2. So just pretend that last couple of minutes didn't happen.
So that is a sheet you can erase, or I wasn't quite sure.
I need one of those blinking eraser things, right? Right, so now you can multiply by the power and reduce the power by 1. And we can square this and add 1. And we end up with 1 plus 1/4x. Are we good? After about the 3rd attempt. With the right question, it wasn't that hard to do. I just not getting into the swing of things yet. Now, the surface area then is going to be the integral from start to finish, which is 0 to 12, of 2 pi x, the square root of 1 plus 1/4 x dx. Now, once you've got to the point here, you got a big decision to make, and that is, what technique am I going to use to integrate it? And it kind of depends on what you get. Sometimes you just get really lucky, right? And it's x cubed plus x, in which case it's a power rule. Wish that would happen all the time, but it doesn't. Sometimes you do integration by parts, and more often than not, don't you end up doing U subs? Do you see that this question is a U sub question? So let's do U subs on it. As you look at this guy, what is the U sub? What U sub will you use in this integral?
One plus 1/4 x.
Agree? Which is basically whatever's inside the square root is a good candidate. I know none of these rules work all the time, but they work a lot of the time, right? So what's in the square root is a good candidate. If you differentiate with respect to x, you get 1/4. If you do the crossover, and if you isolate, you get that guy. I'm going to pull out the 2 pi because I want to. Remove the limits of integration. I'm going to put in x. I'm going to put the square root of u. And then I'm going to do 4 du. Now, I know this hasn't happened often, but it does happen that sometimes you get an orphan left over, a little x. Don't we have to replace that x by something with u's in it? Okay, so watch how I do that. you go over here, your u sub, and you use it by rearranging it so that it becomes x equals. So subtract 1 from both sides, and then multiply both sides by 4. That means, well, let's take care of the 4 and the 2, so that's 8 pi coming out now. That means the x is 4u take away 4. The square root of u becomes u to the half du. What I can now do is distribute the u to the half. And we're now at that point. This we can integrate, which is the whole goal of the u sub, right? Turning something we can't do into something we can do. Would you agree this is just an ugly power rule? Right, just add 1 to the power, divide by the new power. 8 pi is out here. Let's see what we get. If you add 1 to the power, you get 2/5. That gets you 8/5 of that fella. If you add 1 to the power, you get 3/2, and I believe that gets you 8/3. This fella becomes 8/5 square root of u to the power of 5. And this one becomes 8/3 square root of u to the power of 3. Remembering to return back to the x's. And now we can evaluate from x equals 0 to x equals 12. So what do I have? I have 8 pi. Let's go. This fella, 8/5. Let's do something in my head. 1/4 of 12 is 3. 3 add 1 is 4. Square root of 4 is 2. So you get 2 to the power of 5. Take away 8/3. 1/4 of 12 is 3. 3 add 1 is 4. Square root of 4 is 2 again. So you get 2 cubed. Subtract. If you plug in 0 here, you just get 1, so that's 8/5. If you plug in 0 here, you get 1, so that's take away 8/3. Two, 4, 8, 16. Oh God, that's too much work. 8 times 2 to the power of 5 is 256/5. 2, 4, 8, 64/3. Take away an 8/5. Take away an 8/3. Okay, let's see what the calculator does with all that. 256/5. Subtract 64/3. And I caught myself in time. That's not. Take away 8/5. Add 8/3. And then do math. Turn me into a fraction. 464/15, which I can now multiply by 8 to get 3,712/15 pi. That is an ugly answer. And it's actually correct because I have it in front of me here in the solution. Do you see the intricacies all the little details that you need to do just to do one question. That was about 15 minutes. One question. So don't do these homeworks at 5 o'clock in the Sunday afternoon, because just this one section will probably take you the Sunday afternoon, right? So you got to spread these out and get them done as much as you can early in. Are we okay with that question? So this guy here is a candidate for that question, right? So the way I did this one is the way you do all of these guys. So I'm now going to find a question that looks like this and one that looks like this, and they'll take a fair amount of time as well. So I'm looking for a x equals function of y being rotated about the x-axis. Here we go. Question 9. And it looks like this. It's 4x equals y squared plus 12. And we're telling you it's going from 6 to 11. And that it's being rotated about the x-axis. Well, as if it wasn't bad enough doing these questions, this needs a fair amount of tweaking because it's not quite the information the way I need it to be written. Let's do the easy one. If you divide everybody by 4, we now have the g of y to see where we got it. Okay. And I'll be returning to this later. Find its derivative. Oh, not bad. 1 plus its derivative squared. Oh, not too bad, right? Not too shady. Since it is an x as a function of y and it's being rotated about the x-axis, I need to do the integral from c to d of 2 pi y, the square root of all of this. Then I look and it's c to d, which means that I need to know the y coordinates of where you start and finish, not the x coordinates. Do you see up here they've been really annoyingly sneaky? This is what they told me, but this is what I need. You see that? So how can I use the fact that x is 6 to 11 to figure out what the y ranges are going to be? Any suggestions about how I could make that happen? All right, let's take 6. If x is 6, what will the y value be when x is 6? Anything come to mind? Here's some clues. I know this, and I know x is 6, and I want to find y. How could I do that?
Would it be the square root of 12?
Well, very interesting answer. I like it. It's a good answer. Let's show you how you find out. If you know x is 6, then can't you just replace it in here, which is what I'm assuming she must have done. Right, Sarah? You just did it in your head. And that gives you 24. And that gets you 12. And then you take its square root. So this guy is the square root of 12. Now, if you go for 11, right, suppose we make this 11. What this relationship tells us, what this curve is telling me is, if I know x, I can get y, but can't I get y if I know x, right? It works both ways, right? So in this case, 4 lots of 11. And that's 44, which is what, 32? And there. So do you see I had a little side journey where normally you wouldn't have this problem, because normally you would just be told that number and that number, and you wouldn't even need to go hunting for it. Okay, we got to the point where we've written down the integral. Now we have the same decision at the same place. Don't we have to decide what method? Agreed? What method is going to work for this one?
The second one?
Oh, I'm not sure what your question means. We are using this equation. What I'm saying is, if I wanted to find this integral, would I use integration by parts? Would I do a u sub?
U
God
sub.
forbid.
Sorry,
Yes.
I misunderstood.
Well, it was me not phrasing it well. So u sub, which is kind of, I wouldn't say every question's u sub, because they're not. But would you agree there's a lot of u subs going on in these kind of situations? Now, if you differentiate with respect to y, you get a half y. If you do the crossover, you get a half y dy. And if you isolate the dy, you get 2 over y du is dy. Are you happy about the 2 being in the top? Rather than saying 1 over a half y, it just makes, I think 2 over y sounds better. So we're going to have an integral. Okay, I'll stick my 2 pi outside. We're going to have a y. We're going to have a square root of u. And we're going to have a 2 over y du. The y's are going to cancel, and I'm going to use that 2. So now I have 4 pi. And square root of u. Actually, this one's going to be a little bit easier, isn't it? We don't have less work, as much work to do. So it's going to be the integral of u to the half. That's a power rule. So add 1 to the power and divide by the new power. You get that. That's essentially going to get me 8/3 pi. And that's going to become the square root of u cubed. And that becomes this guy cubed. And we can now evaluate it, at y equals the square root of 12 and y equals the square root of 32. Now I go through these questions, I tend to write as many lines as I think I need. I could easily imagine that if you're doing homework, would you agree you could probably miss a couple of these lines out at least? Yeah, I can go from line 3 to 5. I don't need to write number 4 down. Now, in this case, it's going to be 8/3 pi. So let's see what we get. If you plug in y and replace it by the square root of 32, this guy becomes 32. A quarter of 32 is 8. 1 plus 8 is 9, so you get the square root of 9 cubed. If you plug in 12, you get 12, you get 3, you get square root of 4 cubed. And that's 3 and 3 cubes, 27. And that's 2, and 2 cubed is 8. So you get 19. Whoops. And 8 times 19, 152 thirds pi. So that's how you find the surface area when you're given a function in terms of y and you want to rotate it about the x-axis. That took a little bit less than 15 minutes, but you know, let's say on average 15 minutes for each question. Are we cool with this one? Figure out the right formula and then just go through the process. Every question I've done, including the last half hour of Tuesday, you could almost, it's almost like I was just repeating myself, right? I'm doing the same thing over and over again, right? And that's what I mean when I say the process. So that one was what, question 9. So I need to find an x equals function of y that's being rotated about the y-axis. So where are you? Here we go. Question 12. In this question, here is our function, and it's being rotated. Actually, this is 12b, rotated about the y-axis. G of y is good to go. Uh-oh. I don't know where to start with the y. I don't know where to finish with the y. In fact, someone sent me an email with a question where the same thing happened. It happened with x's. And he wanted to know why the limits of integration were 0 to 1 when there was no mention in the question of 0 to 1. And this answer is 0 to 1. But it's not mentioned. That's all that's mentioned. How do I know that its range is 0 up to 1? It's kind of sneaky because they don't even give you a hint that I'm going to do this. But can you see why 0 to 1 would be the only fit? Look at that function. Do you know that it only exists for certain values of y? Because it's only positive for certain values of y. If you plug that into Desmos, which would be a good idea, it would look something like that. I'm not saying it'd look exactly like that. In fact, let me redraw that. It would look like this. And here would be 0 and here would be 1. So can you see that by the basic geometry of the shape, do you see why y has to be 0 to 1? It's the only place where the curve actually exists. It doesn't exist anywhere else. Because for any other value, the numbers inside the square root are negative and they don't exist as real values. So there was a little hiccup, 0 to 1. Back to the question then. If I want to differentiate this, oops, I need to call it that. And the reason I need to do that is that this is a chain rule. So it's 1/2 y take away y squared to the power of -1/2 times the derivative of what's inside the brackets. So the derivative of this guy is that guy. Now I'm going to do style points. 1 minus 2y goes on the top. This 2 goes in the bottom. This half power goes in the bottom and it turns into a square root. Are you comfortable with this becomes that? Right? If you look at each piece, it goes in a certain place because of what it's equal to. Now I'm going to do the derivative squared. If you followed every question I've done over the last, today and on Tuesday, isn't this the kind of approach, right? I start off with the function, I differentiate it, I square it and add 1, and then I try and make it pretty, right? That's exactly what I'm going to do here. So it's going to be 1 plus all of this. When you signed up for Calc 2, we should have said you sign up for Calc 2 plus horrible algebra, right? Because you have to do a lot of algebra, especially in these sections. So 1 plus this guy squared. If you have an expression where there's pieces to it multiplied and divided, you can separate them by squaring them all individually. Are you happy about this guy squared is that guy? 1 minus 2 squared on the top, 2 squared is 4, square root squared, no more square roots. What's going to happen next then? Am I going to leave that or am I going to do stuff?
You could probably foil and then cancel something on the top.
Well, that would be nice. I'm not sure how much cancelling, but what you said is true, but you're just doing it one line too early. What about that 1? Don't we have to take care of that as well, don't we? Which means we are going to have to do this. We're going to have to add them together. And then that thing about foiling, that's exactly what's going to happen next. But this first, foiling second. Right, do you notice all I did with 1 is I called it this guy over itself, and this is the reason, right? They now share a common denominator, which means that sometimes things have to get uglier before they get nicer. Okay, now let's do that foiling and distributing you were talking about. 4y, take away 4y squared, plus 1, take away 4y squared, take away 4y, all over this. I just pause for a minute. Look at the numerator. Wow. Do you see what's happening here? Look at the carnage. That gets killed off by that. This gets killed off. Oops. Did that get killed off? No. Oh. Yeah, now it gets killed off. These two get killed off with these two. And only thing left is a 1. That is so nice. It's so nice. So I can return to the equation. And the equation that we're going to use is this one. So it's the integral from c, which is 0, to d, which is 1, 2 pi g of y, which was this guy, times the square root stuff, which was this guy. See this fella here? This square root of 1 over. Let's try and make it pretty. And I'm not even going to do an awful lot, although I would like to have done more. I'm just pulling out a common factor of y. And you might think, why you're not doing more? Because on the last two questions, you only get to this line and stop. And you get 5 choices to pick, and one of them's this. And I believe this one. Oh, I take it back. Too quick. Got that guy? Actually, I'm finished. I could have finished there. I think it's the 4th circle. I was doing this, but I realized I don't need to. Actually, if I was going to do it, I'd cancel the thing down. It'd be even prettier. So in the last questions, the last 2, you don't need to get the entire answer. You only need to get to a nice integral, right? The simplest version you can get, or actually looking at the ones I'm looking in front of me. I don't even think you take them to here. I think you kind of stop about a couple of lines before you could make it even nicer. And so when you get an integral and it looks like one of the 5, stop, put a circle around it and move on. So that's a little bit less work for the last few. And that would be this fella here, which is number 12. Okay, we're about to move on, unless, do you want me to do another 15-minute or start to finish, or have you seen enough of these guys for the time being? A thumbs up, Fez. We've seen enough then?
Enough.
Okay, right. Well, let's get started on our next section, and it's going to be the last section for today. That doesn't mean we'll be finished early, because I'm sure we won't be, but it does mean that we're doing a totally new thing. And if I can find it for you, here we go. Hopefully, you'll find it a little bit easier. So I'm just getting my heading set up. Math 152, chapter 8.3. Applications. To engineering. So we are actually going to do some stuff that is of practical use, even if though it might be at the beginnings of it. And we're going to show you some interesting things. We're going to start off today with what is called the center of mass. And we're going to do some questions calculating, finding the center of mass of various objects. Has anybody done a physics class where they talk about center of mass? Do you know what I mean by that phrase? Right. Well, it's like a balance point. So I want you to imagine that I have a very thin ruler. And it's so thin and it hardly weighs anything that it's of negligible weight, which is what they do in physics when they want to ignore something. It's of negligible weight, right? Negligible mass. Now on this ruler, oops, it has positions marked on it. And at various points, there are some masses, some weights. Right at the end here, we've got something that weighs 10 pounds. And over here, we've got a second weight and it weighs 20 pounds. And right at the end here, I've got my third weight and it's 5 pounds. Now, the center of mass would be some point between -2 and 4, that if I put my pen on it, it would balance, you know, like a scale. Now, because there are weights here, the center of mass won't be 1, unless we're very, very lucky. Can you see that it might be more to this side or it might be more to that side? And we are going to find this fella called the center of mass. And this particular one is a 1D situation, right? One-dimensional, a line situation. And the center of mass is called X bar. So let me show you some naming that we give. These 3 points, I'm going to call this one X1, that's its position. This one I'm going to call X2, its position. And this one I'm going to call X3. And this one, its mass, so I'll call it M1. The second one's going to have a mass, it's called M2. And the third one's going to have a mass called M3. And now what we're going to do is we're going to calculate 2 things. First thing we're going to calculate is called the total mass, which is what would all of these things added up be? So if you want to see a formula for it, it's simply just add the weights. So 10 add 20, add 5, and the answer is 35. That wasn't too hard. And then we get a thing called the moments. Has anybody taken a physics class and they've heard the word moments? Right. So you multiply the mass with its position. So this is how you calculate the moments. So for this one, it weighs 10 pounds and its position is -2. For this one, it weighs 20 pounds and its position is 1. And for the third one, it weighs 5 pounds and its position is 4. And in this case, you get -20 plus 20 plus 20, and you get a total of 20. And that's called the moments. And the formula for getting the center of mass is the moments divided by the total mass. So 20 divided by 35, keep it simple, 4/5. So 4/5 would be about here. If this was a real piece of wood and on it was these weights, if I put my finger at the position 4/5 and I was strong enough to do it, that would balance, right? So the center of mass is a balance point. Why are balance points important? Well, let's take construction. Let's suppose you've got a roof. And we'll forget about the end points because they're always there. But on this roof, you have three different weights. If the center of mass was somewhere, say, like here, that would be the best place to put a support beam. Because the way the physics works is, if something is connected as it is here, and there's different weights on it, you can think of it as acting on one point, and it acts on the center of mass point. So actually that would be the best place, because if you left that, it would stay put. You might think you would put it under the middle one, but actually if you put it under the middle one, there'd be a slight tendency to lean over to one side, and it would actually be less stable than this. So when they build bridges and they build buildings, one of the things that they look for are the centers of mass of each level and the entire center of mass of the entire object. If you are on a big aircraft carrier, that's an aircraft carrier, the center of mass of a good aircraft carrier, any ship, is in the middle and quite low down. Right, so if you imagine the sea being here, actually it'd be better if it was under the water, but it'll do if it's low down. And that's the most stable position for the center of mass to be. If the center of a mass is too far forward, like there, that ship, as it's traveling through the sea, will dig into the water, and it will be quite unstable, and it may even sink if it's bad weather. And if the center of the mass is away back here, won't it have the opposite effect, that the bow will come out of the water and you'll be doing one of those rocky bouncing journeys, which is pretty bad. So if you've got a small boat and you're into small boats, isn't stowing things in various places helpful to get a good smooth ride? Well, what you might not know what you were doing there, but you were actually moving around the center of mass by moving these things around. And you were trying to get it to go to one particular place if you can. Now, if the center of mass, and it has happened because I've seen pictures of this, have you ever seen those really weird cargo vessels where they pile tons and tons of cargo, typically at a place that just looks unnatural at the front? Right? Those ships, unless you fill ballast, which is basically tanks that you put heavy water into, those guys almost always have a bad center of mass. And what can happen? If they get hit side on and the center of mass is like really high up, if the wind catches it, doesn't act like a sail to push it over? Excuse me. Pushes it over. Big deal. We want to know these guys. And this is how you do a center of mass with a one-dimensional. So let's give you one to try. Here is your shot. We'll make that -5, -4, -3, -2, -1, 0. I guess I should have a 1 here. I'll have a 2, 1 and a 2. And I'm going to put 1 here, and it's going to weigh 15 pounds. Put a second weight here, it's going to weigh 10 pounds. And right at the end, I'm going to do a 40 pounds. You have got 2 minutes, 10 seconds to find the center of mass of that situation. Go for it, no pressure. Just labeling it to make it a little bit easier to figure out who goes where. Got 1 minute to go. Okay. Just getting some new pens. Let's see how these pens work. So you want to find the total mass. Well, what's that? 15, add 10, add 40. And so that's what, 65 pounds? Then we get the moments. Strangely enough, they use the capital word M for moments. I would probably have used it for mass, but they use capital M for moments. And that's going to be M1, X1, mass 2, position 2, mass 3, position 3. In this case, it's 15 times -5, add 10 times -2, add 40 times 2. And that's -65, and that's -20, and this is +80. So we get that. And the centre of mass x bar is the moments over the total mass. And that's -5 over 65, which is about -1/13, which makes it about here, roughly. Why is the centre of mass so far to the right in this question?
Because there's a larger mass on the right side.
Do you see that guy there is causing, is having a big influence? Agreed? And so maybe, I'm glad that that makes sense. So can we call that good? If I give you a piece of wood with some weights on it, you can find the centre of mass and you are happy. So we're now going to do centres of mass in 2D. So 1, 2, 3, -1, -2. So we're imagining that we have some objects in 2 dimensions. So at the point 3, 1, right, that's there. We have a 10-pound weight. Down here, we have a 20-pound weight. And let's say over here, we have a 30-pound weight. Now, if you can imagine that these are joined together to make a triangle, and you don't need the triangle, but imagine that they're there. At the corners of this triangle, and you'll make the triangle out of thin paper that has negligible weight again. The centre of mass would probably be somewhere where my finger is, right? Somewhere about there. There, right? Somewhere in there. Agreed? Now, some of the weights are quite strong, so wouldn't it push towards maybe this corner more than it would be towards that corner? So maybe more like where my pen is now. Would you agree that might be the centre of mass? And the centre of mass in 2D is called x bar, y bar. Does that make sense? It would be an x and a y coordinate. And if the life is sensible, shouldn't calculating it be very similar to how we got x bar? Okay, and a lot of it is. So the first thing we're going to calculate is the total mass, which is I should start labeling these guys, shouldn't I? So this guy here is going to be called x1, y1. That's its coordinates. This guy here is going to be called x2, y2. That's its coordinates at least. And this guy here is going to be called x3, y3. And this fella here is mass 1. Right? This number here is mass 2. And this guy here is mass 3, right? So if I say M3, you know I'm talking about 30 pounds now, right? And if I say X2, Y2, you know I'm talking about this guy over here. Okay. Now the total mass is made up of 20 pounds, 10 pounds, and 30 pounds, which ends up being 60 pounds. Agreed? And we're going to get two different moments. One of them is going to be M1x1 plus M2x2 plus M3x3. And the other one, I don't think it should be a surprise. Would you agree that would make sense, that you would get the moments using the x's and the moments using the y's? Does that make sense to you? Right. So I wish I'd give myself more room, so I'll make it red then. If we start with this one, it weighs 20 pounds and its x-coordinate is 1. This one, it weighs 10 pounds and its x-coordinate is 3. And this one, it weighs 30 pounds and its x-coordinate is -1. And that gets me 20, 50, take away that guy, that gets me 20. Are we okay with the moments of that one being 20? Now, this fella here is 20 pounds and its y-coordinate is -2. This one here is 10 pounds and its y-coordinate is 1. And this one over here is 30 pounds and its y-coordinate is 2. And if we do this one, we get 60, 70, take away 40, we get 30. Now, if I'm going to get x bar and y bar, okay, wouldn't you take this guy here, the 20, right? The moments on the x is 20, and divide it by 60 and get a third. And to get y bar, wouldn't we take all these guys, which is what, 30, divided by 60, and you get a half. And the center of mass then has coordinates 1/2, 1/3, which would make it about here. Does that seem reasonable in the badly drawn picture I've got? That the center of mass would be about here. Now, you might be saying, what are these funny gaps? Why did he do that? And why did they have the same letter? Well, here is some notation which I dislike, but we got to live with it. This fella is called my, and this fella is called mx, which to me sounds back to front. Wouldn't it be much better to call that mx and that my? Because look at how you calculate them, but that's not what they're called. So when you get x bar, it's this guy divided by the total mass, and it's this guy divided by the total mass. And the reason why I had to do this is in your homework questions, they ask you to find big M, right, mx and my. And if you just write down what you think it is, you'll have them in the wrong place. Now, I'm sure there's a very good physics reason for why you call them the way my brain says back to front. I'm not a physics person, right? So to me, that looks kind of weird notation. But can we just live with that notation? That's what they're called, and call it good. So what, well, that's it. Basically, the center of mass would be at position 1/3, 1/2. So let's give you one to try. I guess I'll put it over here. So, got my little guy going on here. Oh, let's make it easier. Well, easier for me. Some of your homework questions don't have pictures. Some of your homework questions look like this. Now, can you see that that is the equivalent to this picture, right? If it helps you, and I guess I should do it because it's only the second question you've seen. Can you imagine that I put, I'll probably have to do a better scale here, 2, -5. So down here at 2, -5, you have a mass of £2. That's this one, right? And then at -3, 1, out here, you have £5. And then at 3, 5, you have your third one, and your third one weighs £3. If you're a visual kind of person, there you go, right? But really, that's all you need. Okay, you got 2.5 minutes to find the center of mass. And do it the way this was done, and you should be fine. I'm just setting up the basic framework. Okay, let's go for it. The total mass is 2 plus 5 plus 3, which is 10 pounds. If you get the moments, the moments around y. What do we get? Well, I'll call this 1, 2, and 3, but you may choose to start somewhere else. So it's £2 with an x position of 2. So that's basically x1, y1. This is x2, y2. And this is x3, y3. And plus a mass of 5 at a position in -3, plus a mass of 3 at position 3. And if you put all that together, we get 4 and 9, 13, take your 2. I get -2. And then if you do this one, it's going to be 2 times the y value -5, plus 5 times the y value of 1, plus 3 with the y value 5. In this case, 15 take away, or 20 take away 10, you get 10. So x bar is that guy divided by the mass. So it's -2/10, which is -1/5. Y bar is the other fella divided by its mass, total mass. And that's 10 divided by 10, which comes out as 1. So the center of mass of this triangle has coordinates -1/5, 1. Let's see what that looks like. -1/5, 1 is about here. So it's quite near that corner, but since that corner is £5, which is almost the same weight as the other two, it kind of makes sense that it might be there. Are we good? Right. So feels like an engineer class. Like, where's the calculus? Let's do the calculus now. Center of mass of a region. Suppose you have a curve y = x², and you're interested in this region here. Now, we make some assumptions. Can you imagine that is a plate and it's the same thickness? So there isn't one specific dot where £5 live. The whole shape weighs something. We are interested in finding the center of mass of this region. And so we are going to show you, I'm going to show you how you go about that. X bar is in terms of an integral. I'm going to get no notation right here. And it's an integral from a to b, 1 to 2 in this case, of x, f of x, dx. And y bar is the integral from a to b, and it's 1/2 f of x squared dx. And there's a 1/a outside. And a is the integral from a to b of f of x dx. So can you think of the a on the bottom as being like the total mass? And this integral in the top, that's like the m of y. So what you have here is basically just formula that you use. So I can find the center of mass. If I'm a gambling person, which actually I am, but shouldn't be, I'm going to go for about 1.7 4, right? That's my guess. Bit hard to judge in my really bad skill. And by the way, it is a guess. You might think, oh God, no, it's 1.5, 9 or something, whatever. Let's find how to do the center of mass of your region. So step one. Find A. Find the total area under the curve. So in this case, it's 1 to 2. Picking a nice easy function because I want to make my life relatively simple. And I get 1/3 times 2 cubed, take away 1/3 times 1 cubed. And that's 8, take away 1. I get 7/3. So step one, find A. Step two, find x bar. It's 1 over A, the integral from A to B of x, f of x, dx. Right, 1 over 7/3 is the same thing as 3/7. You happy about 1 over 7/3 is just 3/7? Right, reciprocals. The integral from 1 to 2 of x times x squared. Again, I'm keeping the integral really nice, nothing too scary. It's going to be the integral from 1 to 2 of x cubed. And that's going to be power rule. What does that get me? Well, if you plug in 2, you get 1/4 2 to the 4, take away 1/4 1 to the 4, 2, 4, 8, 16, take away 1/15. So you get 15/4, which is 45/28. And I said 1.7, didn't I, in my guess? So 45 divided by 28. Am I good at guessing, or am I good at guessing? I wasn't that far away. So far, so good. Now, you know what step 3 is going to be, isn't it? Find y bar. Right, so not going to be too much surprise there. So step 3, find y bar, which is this integral. Now you're just trusting us. We just tell you these formulas just like they do in physics or whatever, and you just say, okay, I don't know why that does what it does, but I'll trust you. Actually, if you ever get to do Calc 4 with me, I can prove this to you. But right now, you're just going to have to live with it, right? So 1 over A gets us the 3/7 again. The integral from 1 to 2 of 1/2. This particular function, what was x squared? Squared. I'll bring that half outside, so it's now 3/14. The integral from 1 to 2 of x to the 4. And we have a power rule. Okay, plug in 2 here. You're going to get 1/5, 2 to the power of 5, take away 1/5, 1 to the power of 5. 2, 4, 8, 16, 32, take away 1, 31/5. That's going to be 93/70. And what did I say is my guess? 4. Ugh. I'm not looking so accurate this time. I was miles off the second one. So the center of mass of this particular guy was 45 28ths, 93 70ths. But doesn't that mean that we now have a way of finding the centre mass of any weird shape you like? Now, if you're trying to visualize, what does that centre mass mean? Can you imagine you made a piece of metal that shape and I had it in my hand? If I stuck my finger right under where that centre mass dot is, and I was really good at it, that piece of metal would be balanced. It would stay there. Have you ever seen circus performers where they balance some weird things with really ugly, awkward shapes? If you watch really carefully, every single thing that they are balancing, they are making sure that their head or their foot or their hand, whatever it is they're using, is directly underneath the centre mass of that particular shape. And it's a clever trick to be able to have the ability to do that, because it's not obvious where the centre of a mass of a shape is. I'm pretty sure they don't do Calc 2 in their head while they're figuring out how to balance it, but that's how we would be able to figure it out. So far, so good. Agreed? Are you happy about centre mass of a single integral? So I'm going to have to up it one more level. Suppose you have two functions, one called x squared and the other called the square root of x. And the shapes look like this. So this is the square root of x and this is x squared. And we're being asked to find the centre mass of that shape. Now, can you see it's the area between two curves rather than the area under a curve? Agreed? Now, that means that we have to adapt how we do the question, okay? Because it's not one function anymore, isn't it? Two different functions. And I'm going to call this fella f of x, and I'm going to call this guy g of x. Okay, now if you're wondering why I chose this one, if you draw this one in red for a minute, just to make it different, isn't this one higher up than that one? So shouldn't this one come first and the other one come second? So I like f to be first and g to be second, so that's why I did it. Now, the area of this shape is the integral from a to b, and won't it be f of x take away g of x? Can you remember doing areas between curves? Isn't that how you find them? And don't you need to know top guy take away bottom guy? That's why I did what I just did there. And x bar then and y bar have to be adapted. Well, x bar is going to be 1 over a, the integral from a to b, some stuff, dx. How do you think I'm going to adapt x f of x to this new world? What would the formula change to when it's the area between two curves that we're getting the centre of mass of? Are you too shy to tell me?
X squared? I don't know.
Don't do it. I'll cover this. I want this guy going away. Right, cover that up so he doesn't distract you. Cover that up. That's it. Top one. X f of x. The area is now a difference. Does that make sense? Agreed? Right. Now, the other guy. there are two, I think anyway, there are two possible answers to this. Obviously one's wrong and the other's right, but I don't mind if you get the wrong one. But could you have a guess at what you think this equation develops into?
Just f of x minus g of x squared.
Right? And the alternate would be that one. Now, do you notice it's not subtract them first and square the answer? It's square them first and subtract the answer. But that's the only two that are out there. And I did ask for either one and I got one. Right? So you just have to make sure that you remember the adapted situation and we should be able to get it. Now, that guy there is 0 and that guy there is 1. Can we do that? It's kind of obvious, you know, but if I needed to, when I solve, when are they equal and get the answer. Right. So I got my A and my B. So the area is the integral from 0 to 1, f of x, which is the red guy, take away g of x, which is the other guy. So that's going to be the integral from 0 to 1. And probably about the 20th time in our life, we have a x to the half to integrate. Add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. And evaluate from x equals 0 to x equals 1. In this case, because the number's 1, I don't need to be too clever about making that look pretty. It's 2/3 times 1, take away 1/3 times 1 cubed, minus a whole load of zeros. And 1 to the power of 3/2 is still 1, so you get 2/3, and that is 1/3. And the answer we get is that it's a third. So the area between those two guys is 1/3. That's good. Good start. Step 2 is get x bar. It's 1 over a, the integral from a to b of x, f of x take away g of x, dx. Now we know a is a third, so 1 over a gets you 3, right? 1 over a third. From 0 to 1, x, and f of x in this case was the square root of x, take away x squared. So that's what we're working with. That's what we're working on. Help me out here. I can't integrate that yet. I got to do some stuff, right? I can't just leave it like that. I need to fix it. Help me out here. What do I do next?
Distribute.
I hear it. Can I call that x to a half without writing it down? So x times x to the half gets you 3/2, and x times x squared gets you x cubed. Now that I've done that, can't we just use the power rule? So add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. Evaluate it at 0 and at 1. If you plug in 1 here, you get 2/5. Plug in 1 here, you'll get 1/4. Take away a whole load of zeros. I have 2/5. Take away a quarter. Just do the whole thing in the calculator then. So it's going to be 3 times, put a bracket around it, 2/5, subtract 1/4. And then math 1 to make it a fraction. And I get 9/20. Okay, we now know the X bar 9/20. A bit surprised by that. Yeah, maybe not. I mean, it's almost halfway, isn't it? I mean, 10/20 is halfway. It's pretty close to halfway, so maybe I shouldn't be so surprised. Let's get Y bar. It's got its formula. Oops. 1/2 f of x squared, take away g of x squared. So you square them first and subtract them second, right? So that's a third, so you get 3, 0 to 1, 1/2. F of x is the square root of x, and you square it. G of x was x squared, and you square it, dx. Might as well bring that half out. That guy gets you x, and this guy gets you x to the 4. So that's what you end up with. 3/2 this integral. This is a power rule. Add 1 to the power, divide by the new power. And let's see what you get. You get 1/2 times 1 squared, take away 1/5 times 1 to the 5, take away a whole of the nothings. You get 1/2, take away 1/5, and you get 9/20. So the center of mass is actually 9/20, comma 9/20. And then if I look at this shape, would you agree that if you cut it with this straight line, I know I've drawn it badly, but wouldn't that be equal halves either side of that line? Do you see it's kind of balanced? So it's not a surprise then, isn't it, that the center of mass has the same x and y coordinate? To me anyway, it's not a surprise. It's a little bit of surprise that it's not exactly in the middle, which is where 10/20 is. It's actually a little bit, you know, about here, a little bit to the shyer side. Anybody want to chuck in an idea? Because I can't think of one. Why it's not exactly a half? It just is, I guess. I don't know. Maybe it's fatter at the beginning and skinnier at the end, right? Maybe it's a banana that's got a little bit of shape to it.
Maybe you didn't draw it right.
Oh, that is possible. And if I'd drawn it better, I might have saw that it wasn't quite in the middle. That is not very nice, but also true. Are we good with finding the area, so far anyway, finding the center of mass of the area between two curves? Are we good so far? I'm putting down Ryan's name on remember to take 10% off his next test. So you got to get a brownie point back before today's finished so it can cancel this out. Okay. What shall I do? I still want to do another one of these guys. If possible, I would like to do a few more of these guys, but I'm trying to find one that's kind of nice. Yes. Okay. I'm not doing question 7. I just want to set it up. Basically, the question just says, find that, right? So they don't tell you much. What's different about this guy, and this is basically all I want to do, is to set this thing up. You know, you can plug that guy into Desmos and he'll look like that. If I rearrange this fella, right? If I rearrange this expression here, won't y be the fourth root of x. Are you happy about how I did that? So it's going to look something like that. Actually, isn't that very similar to the one we did with x squared and the square root of x, right? You're going to have uglier fractions. Now, the shape that we're going to do it to is this fella. Don't I need to know that x value? That one I'm pretty sure is 0. It shouldn't take much to figure this out. Would you agree it's 1 again? Okay, pretty much isn't that question good to go? And it's almost the same as the one I did. So that's as far as I want to do that one. Next one is like question 8. And you're being asked that, right? So what would I do? I would go to Desmos and I'd make sure that, you know, we got something like this. And I would draw the sine function, and it would look maybe something like that. Oops. And I do the cosine function and it looks something like that. No, it won't be there. Let me redo that guy. I'll just do a lot of the sine function. I won't need anywhere near as much as that. I'm going to do the cosine function. I won't need really any as much as that. And then I would do the guy that we're talking about, and he happens to be here. And x equals 0. What line is x equals 0?
The y-axis?
Yes, it is. So see this shape here that looks like an axe head to me? That's the shape that we're trying to get the center of mass of. And I think you really do need to visualize this, because now that I've got that picture, can you see that the red guy, which is the cosine one, is my f of x, right? It's higher up than the other one, which is the blue one, right? So when I'm looking at this function, I can see that this fella here is 2 cosine 3x, and he's high. And the blue one is 2 sine 3x. So this is not going to be really that much different than a lot of the questions that we've done. The main issue is probably going to be trig functions, which I know are you love trig functions, right? So let's get the area between these two curves. It's 0 to pi upon 12, mostly because they told me, right? That's what that's about. And it should be f of x, take away g of x, right? The area between two curves. And it's 0 to pi upon 12. And the f of x is 2 cosine 3x. Subtract 2 sine 3x. Pause for a minute. Are we happy about my setup for the area between the two curves? Are you happy why it's cosine first, sine second, so forth, right? Now, you want to integrate these guys. And you're going to evaluate it from 0 to pi upon 12. Aren't these good for the linear shortcut method, right? Otherwise, don't have to do a u sub, and that takes forever. So if you integrate a cosine, you get a sine, agreed? So if you integrate 2 cosines, you get 2 sines. What does that 3x get you when you do the linear shortcut method? What does that 3x get you?
1/3.
So are you happy with 2/3 sine 3x is the integral of that guy? You happy where I got the 3 from? Right. Now, if you don't like that, do a U sub on some scratch paper, and this is what's will come back. Now, if you do a sine, don't you get a negative? So that's plus. Are you happy about the plus and the 2/3 cosine 3x? Same kind of reasoning that we did for the first trick. Good. Now, we are going to find the area between these two curves. Don't expect 3/4 or a half. Expect ugly, because more times than not, that's what you get, right? Ugly. So, 2/3, the sine. Okay, I'm going to do something in my head. 3 times a 12 gets you 1/4 pi. Plus 2/3 the cosine of a 1/4 pi. Take away, isn't the sine of 0 still 0? So I'll just write nothing there. But what is the cosine of 0? Right, when you plug 0 in here, you get 2/3 cosine 0. 2/3, what number is the cosine of 0?
1.
1. So you get 0 plus 2/3. Now, a different question, again to do with exact values. What is the exact value of the sine of pi over 4? And don't tell me it's 0.707, because that's what it is as a decimal. What is it as an exact value? Unit, circle, whatever.
√2/2.
Agreed. And isn't the other one also one of the few times where they're both the same? Take away 2/3. Well, 2 of these plus 2 of these gets me 4, but the 2's cancel, so I guess I get 1/3 and 1/3. So at the end of the day, are you happy where the 2/3 are coming from? I can have 4/6 and simplify it to 2/3. Oh, and take away 2/3. And for style points, I would probably factor out the 2/3. Are you happy about the area between the two curves being that ugly mess? Now, well, I guess this will be the last question, but that's fine. We're now going to get x bar. It's 1/a, the integral from a to b of x, f of x, take away g of x, dx. 1/, that ugly mess. I really can't do much to make it look pretty. That's what I got. It's going to be the integral from 0 to pi over 12 x, and I have a 2 cosine 3x, and I have a take away 2 sine 3x dx. I do not like the looks of this guy, do you? Nothing about this looks pretty. Okay, so it's going to be, oh, I can do something. You happy about the 3 turning up on the top? It's not much of an improvement, but I'll do it. The integral from 0 to pi over 12, 2x cosine of 3x, take away 2x, the sine of 3x, dx. Right, so I just distributed the x's to get this, and I done that 3 on the top. Since there's no nice way to do this, Can you see what I'm doing here is just splitting it into two separate integrals? And each one of these integrals, we're going to find what they are. So at the side, forgetting about all the other stuff that's going on around it, let's just focus on one thing. Getting that guy. Power rule, trig identity, U sub, or integration by parts. That's pretty much the list. Right? Trig identity, U sub, integration by parts. Which one?
Integration by parts.
Agreed. What was it about that shape that made you think that and not anything else?
It's two functions multiplied together.
Right. So we'll call this F and we'll call this G, right? And according to integration by parts then, isn't the answer F big G, take away the integral of F dashed big G dx? Leave the first guy alone. If you integrate a cosine of 3x, you get 1/3 the sine of 3x. We've already figured that out. If you differentiate 2x, you get 2. If you integrate it, you still get this guy. That gets me 2/3 x, the sine of 3x. This guy here gets me 2/3 the sine of 3x. This fella, you can do the linear shortcut method. If you integrate a sine, you get a negative cosine. That now becomes a plus. You'll get extra, oops, you don't need that. You'll get an extra third, which is why you got not 2/3 now, but 2/9. And we can evaluate that at 0 and at pi over 12. So 2/3 pi over 12, the sine of a quarter pi, plus 2/9, the cosine of a quarter pi. Take away. That guy's going to get you 0. That guy's going to get you a 1. So essentially that. This cancels and you get pi over 18. This fella is root 2 over 2. This guy's going to get 2/9, root 2 over 2, and this guy is going to get you 2/9. Would you agree that is a pretty ugly answer? So it's 3 over this guy. This first integral is, well, I can bring the 2's together, I guess. So what do I get? Pi root 2 over 36 plus root 2 over 9, take away 2/9. Subtract. And then I do the exact same thing with the second one, which I should have time to do. And the second one is that guy. And he is also integration by parts. So you get 2x. When you integrate this fella, you get a negative 1/3 cosine of 3x. Subtract, differentiate, you get 2. Integrate, you get another a negative cosine of 3x. Negative 2/3 x cosine 3x. 2 negatives make it a plus. You get that. We have this fella. And integrating a cosine gets you positive plus an extra 1/3, so you get 2/9. that guy. Evaluated from 0 to pi over 12. Negative 2/3 pi over 12, the cosine of a quarter pi. Add 2/9 the sine of a quarter pi. Take away 0 and 0, so take away a lot of zeros. This cancels down as negative pi over 18 root 2 over 2 plus 2/9 root 2 over 2. That gets me not an awful lot, actually. Don't really get to cancel anything. So what do I get? I get this guy over 36 plus this guy. And that goes here. So negative pi over root 2 36 plus 1/9 root 2. So what do I get? I get this fella plus this fella. Take away this guy. Take away adds this guy. Take away this guy. The only decent thing that came out of it was this gets cancelled by that, and that these two add. So you now have this fella. Two of these gets you pi over 18 root 2. Take away 2/9. And that was just X bar. I do not have enough time to do Y bar, at least in full. So I'll just start off what Y bar would look like, and I'll just have to leave it there. So to get Y bar, it's going to be 1 over A, the integral from A to B, 1/2 f of x squared, take away g of x squared. And we already know that this fella ends up being that guy. And the integral was 0 to pi over 12. Might as well bring that a half out. So if I bring the half out, that's a quarter. If you take the two guys that we have got, I've lost the place here. What do we have? Is it a cosine? There we go. So we're going to have 2 cosine of 3x squared, take away 2 sine of 3x squared. That's 4 cos squared 3x's, take away 4 sine squared 3x. Ah, something interesting's happening. Do you notice that you can pull out a common factor of 4 here? Doesn't look like particularly helpful, but it is actually. I'm pulling that 4 out and it's going to cancel with this 4 on the bottom. So we now have a slightly nicer looking guy here. And we've got this fella. And now I'm going to do some magic. I didn't think I'd get this finished, but pretty much I'm going to almost finish it. Whoa, where did that come from? Cos squared 3x take away sine squared 3x is cosine of 6x. Right? That's a magician. I just pulled that out of a hat somewhere. Any ideas where I got that from? I got it from this identity here. Does anyone know what cos squared x minus sine squared x is equal to? It's one of the identities that we rarely use, but it is an identity we should know.
Is it just one?
If it was a plus, it would be just 1.
Cosine 2x?
Yes. And you might say, well, how does that help me? Well, cos squared 3x take away sine squared 3x will be the cosine of 2 lots of 3x. In other words, 6x. Now, would you agree that's pretty easy to integrate, although I don't have time to do it? Then plug in your 0 and your pi upon 12, and you've got your y bar and you are finished. We almost got to the end, but time got the better of me. Okay. Say hi and bye-bye. I'll hang about for any questions.